Well, things are really starting to soften up out here. The snow covering the ice is getting kind of soft and mushy. It's the end of March, March 31st. It's about 3 p.m. It's actually pretty nice out. If you're in town, it's pretty warm, but you come out here, the wind coming off the ice, coming off the lake, it's kind of cool. So I'm up on high ground now where we can get a good look at things. Well, let's see. Lake Superior is 600 feet above sea level. I climbed up a bit, and so I'd estimate I'm good. An extra 200 feet up. And this is what you call a talus base. All the fallen rock on a cliff. Aha, critter tracks. I have no idea what that is. Probably a porcupine in that little cave. Yeah, bit of a cave there. Yeah, wouldn't surprise me if there's some porcupines dwelling in that right now. They're waiting to come out at night. Well, I feel like a mountain goat. Whew. You know, that's tempting to climb, but oh geez, that's a long ways up. All right, it's only been maybe a couple of days since I been out here. What was a 3-foot fissure in the ice is now way wide open. You'll see open water, and across this open water that's as much wider now. That ice on the other side of this open water is moving right now. There you go. Nice big crack. At any time, this is going to let go. So no, you don't want to stand on the other side of it. Because judging by this crack, yep, we're going to have a big hunk ready to break off any second now. Could happen within the next, I don't know, could happen in about 10 minutes from now. 3 days from now. So no, I don't think you want to watch me taking off on a nice flow waving goodbye to you. Now what's happening right now, the ice is transferring heat energy downwards. When we're looking at sub-zero temperatures outside, say about minus 20, minus 25 Celsius, heat energy will be transferred from the water through the ice into the atmosphere, and the ice will start getting thicker. The water underneath could be +1 or as much as +5 degrees Celsius. But right now, the air temperature is about, it feels like about, I don't know, it feels like about +7 or 8 degrees Celsius. That means that heat energy is transferred the opposite way. It is now being transferred downwards into the water. And with the water temperature about, well, only about maybe 2 degrees above freezing, it'll start to erode the ice and make it thinner. But normally in the winter time with sub-zero temperatures, you could say the top 80% of the ice is very, very cold, where the bottom portion of the ice could be just a little colder than the water, like about -3 degrees Celsius. So erosion can happen underneath, given the right circumstances. It also depends on the flow, or the flow energy of the water. You may get submarine land features, or depends on the topography underwater. You could have a small valley underwater which could focus flow energy of the water, causing more erosion. You could also have tributaries coming from land, like rivers, into the water. There's more flow energy there. That too could erode the ice or prevent it from getting thick. When this all starts to freeze over, it's actually called border ice, meaning it starts from the shoreline and works its way out. That's because near the shoreline it's more shallow. It actually means there's a smaller amount of heat energy to be dissipated into the atmosphere, and it will turn to ice quicker than out in the wide open middle, or the farther out you go. Now if we had normal conditions and this ice is really good and thick, like with no interruptions in the freeze over, such as abnormally warm temperatures, say middle of February, you could walk for quite a distance out here. But all that ice is not one single sheet. It's almost like tectonic plate action on the Earth. Each section, or these big sections, are like, well, they're hundreds of square miles, and they're always on the move. And you're looking at thousands of tons of ice on the move. When they start ramming together, you get what's called pressure cracks. Now, pressure cracks can be like miles and miles long, or you could get fractures from all this movement, not just on the edge of all these plates, or gigantic sections. You have to remember, ice is not malleable, it's kind of brittle. So when it gets heaved around, it has no choice but to crack. So pressure cracks can be like very massive and very, very long, or they could be intermittent and a couple of 100 yards long. And also, when you look at the ice really close, like if you got crystal clear ice, and you look at it really closely, you'll see microfractures in the ice. That can happen from temperature or thermal shock, because you could get rapid heat dissipation through the atmosphere or through the water. You could get a surge of abnormally warm water underneath that ice that happens to be super chilled. It's kind of the same thing as taking an ice cube and you plop it into a beverage, you hear the ice crack, and that's thermal shock. Now, ice can undergo thermal shock under the right conditions. There could also be, well, the atmosphere could change. It could rise a matter of 10 degrees in less than 12 hours. And the shock isn't immediate, and the crack doesn't, or the fractures don't happen immediately, but within a couple of hours, the rapid temperature change near the surface can cause that thermal shock, whereas also thermal shock can occur from super chilled ice getting abnormally warm water underflowing it. Another thing that can have an effect on the ice is atmospheric pressure. Now, ice is very much oxygenated. It all depends on the water movement. You could have water where it's out in the middle, where it's open. High winds can stir up the water. It can be more oxygenated. And that underflows the ice. That water that has more oxygen will cause the ice to be it'll be less opaque. Actually more opaque instead of clear. The more oxygenated the water is, the more opacity you're going to have, and it's going to be hard to see through instead of being crystal clear. But also, with that oxygen being in the ice, when you get a change in atmospheric temperature, or no pressure, it will want to expand, and that too could change, or it could cause it to want to fracture because it's exerting pressure on itself. So you have to remember that there's oxygen in that ice. When you get changes in atmospheric pressure, that can have an effect on it. Now, as for the surface of the ice, that can undergo a lot of changes too. We start with above normal temperatures, like wet snow. All that ice that's, well, you could be skating on it. You could get out your ice skates, skate for miles. Crystal clear, smooth. And then along comes warmer temperatures and wet snow. Well, around here, that only lasts for about 12 to 18 hours. We might get above normal temperatures during the wintertime, giving us wet snow. You might even get rain, but that happens once in a while. All that's going to do is wet the ice. And after a while, you look at the ice surface after the next day when the freezing temperatures come back, and it's all rippled, because if you get enough rain wetting the ice, that as it's freezing, the high winds cause it to be all ripply, and then you come out the next day and it's all frozen ripples. As for wet snow, it will stick to the ice as compared to powdery snow that blows across it. So the next day you come out here with your skates and it's all crunchy, rough, and frozen. A lot easier to walk on instead of wiping out all over the place, and it might be about 2 inches of wet snow, but over time it will meld into the ice. It won't be as crunchy. It'll have a texture like concrete, kind of rough. But normally what we get is, well, out here it's kind of patchy. So it was probably drifting snow that was blowing around. Warmer temperatures cause it to like meld into the ice and become more of a flat surface. But if you do get accumulation of soft powdery snow, what can happen is you get an onshore wind that's very high. The skies could be clear, and that'll form blizzards on land, and the highways could be closed because of that. Like, there's no cloud coverage, there's just a lot of high wind, and what accumulates on the ice gets all blown off. And another type of snow is that very super chilled snow. It's not flakes, it's kind of like little ice crystals. That will tend to pack as it's drifting, and it'll pretty much stay there all year. So yeah, the surface could change or undergo a lot of changes throughout the whole season. Now another thing about the ice, the thickness is never the same. Sure, it's flat on top, but underneath it's all lumpy like that. And that all depends on where more heat energy has been dissipated. Now the water is not the same temperature all the way across the whole lake. It can range from 1 degree above Celsius to about maybe 5 degrees at the most. Where there's more heat energy to be dissipated, it won't get as thick, whereas there's less. This lake is very big, so the air temperature is not the same everywhere you go. Also, you got flow energy of the water. It could erode in some places, or it could be allowed to get thicker in some places. Now the unevenness of the bottom, that helps move the ice around, or it can contribute to the movement of the ice. Because of that rough surface, the flow energy of the water has something to push on, whereas if it was flat, it would be just a laminar flow like that, and a uniform flow of water. But the unevenness also gives that flow energy something to push on. Well, a bit of rock climbing, a bit of ice walking, and a little bit of iceology.